Hello everyone, welcome back to Math with Allison. Today we're finishing up our sequences and series, so we're going to be doing the second exam. So this is the third exam of the calculus series. It is right before the final exam, and yes, this was a real exam that was given to students. It is currently given to students as study material to prep for their upcoming exam. So we're going to go through it. We're going to talk about strategies about like approaching problems, what you can recognize and stuff like that. So question 1, we want to use a convergence test of your choice to determine whether the series converges or diverges. Now notice here we have a rational function. Something you can always try is you can always start with the divergence test. So that's where we take the limit as k approaches infinity of our terms. So not the absolute value. We get k over 100 plus 100k. So when we're working with a limit at infinity, we can just take the highest powers of both the numerator and the denominator, right? Because they're basically going to behave the same when we're working with really large k values. So that's k over 100k, which we know simplifies to the limit as k approaches infinity of 1 over 100. And when you take the limit of a constant, it's just equal to that constant. So with the divergence test, what does this tell us? Where if we get a value that's not equal to 0, this literally tells us that it diverges. So this series diverges. That's why divergence test is useful. That's pretty short and sweet. Let's go ahead and try problem 2. So we want to use the convergence test of your choice to determine whether the following series converges or diverges. So again, notice what we have here. We have a rational function. So again, you could try the divergence test. We're going to take the limit as k approaches infinity of k plus 1 over k squared minus 1. So it's always great to try this first because it could be short and sweet. So notice the denominator, we could factor that to k plus 1 times k minus 1. So we get the limit as k approaches infinity of 1 over k minus 1. But as k approaches infinity, this is going to go to 0. So the divergence test is inconclusive, which tells us we need to try something else. Which I suggest maybe we just simplify the series. So we have a summation k equals 2 to infinity. This is going to be k plus 1. Let's go ahead and factor the denominator. We get k plus 1 times k minus 1. This is equal to the series k equals 2 to infinity. We get that k plus 1 cancels, and we're left with 1 over k minus 1. This is really close to the harmonic series. The harmonic series is 1 over k, but the index is starting at 1. So let's go ahead and subtract 1 from the index, which means I add 1 everywhere else to k. So this is equal to the summation k equals 1 to infinity of 1 over k, which this is the harmonic series, which we know diverges. That's not something you necessarily need to prove on an exam. If you know it's a harmonic series, you can show that it diverges. But again, it depends on your professor, so go ahead and ask them. If you're not happy with that, you could try something like the limit comparison test. Or you could try like the integral test if you really wanted to. Whenever you have a rational function, you can try anything of, any of these. They're all going to end up with the exact same result. You could also just try the comparison test. But for now, I'm just going to try reworking the series so we can see that it's the harmonic series. Okay, so we have given the function 2x over 1 minus 3x. We want to go ahead and find the coefficients of the Maclaurin series expansion. And we can use any valid method. So normally, what is the Maclaurin series? It's going to be f of a. In this case, it's going to be x is equal to 0 plus the first derivative times x. So I'm just going to write times x plus the second derivative evaluated at 0 over 2 factorial times x squared plus the third derivative evaluated at 0 over 3 factorial x cubed plus dot dot dot. That's going to help us find our first values. One way you can do this is straight up by finding all the derivatives and plugging in x equals 0. I'm going to show us another way to do this. We can rewrite the function as 1 over 1 minus 3 minus x. And this right here is like a geometric series, a over 1 minus r. So we get 2x times the summation, k equals 0 to infinity. And that's going to be a, which is equal to 1, so I won't write it, but 3x to the power of k. So let's go ahead and try to rewrite this because we have that 2x on the outside. We can fill in our series, right? So we get 3x to the power of 0 is equal to 1, plus 3x to the power of 1 is just 3x, plus we get, that's going to be 9x squared, plus 27x cubed, plus dot, dot, dot. So this is equal to 2x plus 6x squared, plus that's going to be 18x to the power of 3, plus 54x to the power of 4. So notice here what we want to find. We want to find c naught plus c1x plus c2x squared. So the trick here is knowing what c naught is equal to. That is equal to 0. That's the term that doesn't have any x's. And then we get c1 is with the x term, so 2. C2 is equal to 6, and C3 is equal to 18. And that's what the problem was asking you to find. It was asking you to find those coefficients. So now if you forget the geometric series little trick that I just did right there, then another method is you can straight up just find the derivatives, plug in x equals 0, compute it out. And you will end up with the exact same thing. So great practice for you if you want to try it out. Okay, so here we have another series. We want to figure out if it absolutely converges, conditionally converges, or if it diverges. So what we need to do here is we need to try both series. We need to try the absolute value of the series, so k equals 1 to infinity. That's going to take away that alternating portion of it. We want to see if that converges or diverges, and we also want to see if our normal series converges or diverges. So really, let's go ahead and rewrite it so we can see what kind of trick we want to use here. This is going to be like 1 over the square root of 2 times 1 over the square root of k. So we have 1 over the square root of k is equal to 1 over k to the 1/2, which means we can apply the p series test. So in our case, the exponent p is equal to 1/2, which is less than 1, which tells us that this is going to diverge. So right now what we know is the absolute value of the series diverges. Now let's go ahead and see if the normal series converges or diverges. We're going to use the alternating series test, and the clue here is we have that -1 to the k plus 1. When we have that alternating portion, you can apply the alternating series test. So we take our terms without the -1 portion. So we get rid of that. We get 1 over the square root of 2k. The first thing we want to show is that this is decreasing. We know this is decreasing because the k is in the denominator, so it's going to get smaller and smaller. The other thing we want is the limit as k approaches infinity of our term goes to 0, which does indeed go to 0. Since both of these are satisfied, we know that this is going to converge by the alternating series test. So now let's put these together. We know it converges when we have the alternating portion. When we get rid of that alternating portion, it's going to diverge. So this is going to converge conditionally. Now, if it was to diverge, both series would diverge. If it was to converge absolutely, both of these would converge. Question 5, we want to consider the power series, and for part A, we want to determine the radius of convergence of the power series. Keyword, radius of convergence, ratio test, radius, ratio, radius, ratio. We want to take the limit as k approaches infinity. We're going to take our k plus 1 term, so it's going to be x minus 2 to the k plus 1 divided by 3k plus 1 plus 1. I'm adding 1 to k, right? You can totally just write this as k plus 2 though. K plus 2. Then we divide by the normal kth term, and I'm just going to multiply by the reciprocal. So 3k plus 1 divided by x minus 2 to the k. So let's go ahead and see what cancels out. This x minus 2 to the k cancels out. That just leaves one of them in the numerator. We get k plus 1 terms cancel out, and that's just going to leave us with 3 to the power of 1 in the denominator. So here we get the limit as k approaches infinity. We get x minus 2 over 3. We don't even have any k terms anymore. So this is just going to be equal to x minus 2 divided by 3. Now, how do we find the radius? Remember, for the ratio test to converge, this is going to be less than 1. We find the radius by just making the x term by itself. I'm going to do that by multiplying both sides by 3. Now I have my x term all by itself, and whatever it's less than is going to be the radius of convergence. So the radius of convergence in this case is equal to 3. Next, we want to determine whether the series converges at the right-hand endpoint. So let's go ahead and continue working this out. X minus 2 is less than 3. That means negative x minus 2 is less than 3, and it means x minus 2 is less than 3. So if I multiply on this left-hand side by negative 1, x minus 2 is greater than negative 3. Add 2 to both sides, x is greater than negative 1. So that's the left endpoint, right? We get negative 1. Now here we just got to add 2 to both sides, so we get x is less than 5. So this is between negative 1 and 5. Notice this has a radius of 3, right? We have that the total distance between negative 1 and 5 is equal to 6. 6 divided by 2 is equal to 3. Anyhow, we want to see if it converges at x is equal to 5. So let's go ahead and plug that into our series. I don't even remember. Okay, so I plugged in x is equal to 5. We know what 5 minus 2 is equal to. That's equal to 3 to the k. And notice those 3 to the k's are going to cancel out. So we get the summation k equals 0 to infinity of 1 over 3. What is this equal to? It's equal to 1/3 plus 1/3 plus 1/3 forever, forever, forever. That is obviously going to diverge. We're just forever adding 1/3. You don't need a test to show that. You just need to understand what the summation of 1/3 is, right? If you want to write out your feelings about it, you can also totally do that. Given the power series representation for 1 over 1 plus 2x, they show us what it's equal to. And this is going to be for 2x less than 1, right? Because this is like a geometric series. It converges when the radius is less than 1. We want to write the first 3 terms of the power series representation of natural log of 1 plus 2x. So let's start with what they give us. This is equal to 1 minus 2x plus 4x squared minus dot, dot, dot. Now, what's the relationship between 1 over 1 plus 2x and the natural log of 1 plus 2x? It is the antiderivative. So what we're going to do is we're going to go ahead and integrate both sides in terms of x. So let's go ahead and do the left-hand side. We get 1/2 natural log of 1 plus 2x is equal to x minus x squared plus, what is that, 4/3 x cubed minus dot, 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 plus some constant c because we're integrating. Now I want to just find natural log of 1 plus 2x. So what do I need to do? I need to multiply both sides by 2. 2 times, that way I get natural log of 1 plus 2x is equal to 2x minus 2x squared plus 8/3 x cubed minus blah, blah, blah plus some c. Now I just found the first 3 terms, right? This right here is our first 3 terms. You just had to recognize that we had to integrate in this case. Now, this is like a bit of a trick question. What is the radius of convergence of our power series in part A? The radius of convergence is going to be the same as the normal series. When you integrate or differentiate, it's not going to change the x values for which it converges for. So here we have 2x minus 1. So what I need to do is I need to get x all by itself. So I'm going to divide both sides by 2. The absolute value of x is less than 1/2. So our radius of convergence is indeed equal to 1/2. That one was a bit tricky. You'll never believe it. This is our last question. We've gone through this quickly. So question 7, we want to find the first 2 non-zero terms of the Maclaurin series, so that's the Taylor series under dot 0, for our wonderful function cosine of 3x. This is going to be very helpful if you know the power series or the Maclaurin series for cosine. So I'm just going to write this out as cosine of y is equal to the summation k equals 0 to infinity of, that's going to be negative 1 to the power of k times x to the 2k. Ooh, sorry, we used y. Ooh, tricking me. Y to the 2k divided by 2k factorial. I always remember the difference between cosine and sine because cosine is an even function, sine's an odd function. So here we get even terms. So what happens when we have 3x? We just replace everywhere we have a y with 3x. So let's go ahead and do that. And now we can actually just write out the terms. So let's go and write it out. So we get k is equal to 0. We get positive 1. We just get positive 1. Yep. Everything is times 0. Raise to the power of 0. It's going to be 1. Okay, minus. So k equals 1. Now we get 3x to the power of 2 divided by, that's going to be 2 factorial, plus 3x to the power of 4 divided by 4 factorial minus blah, 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 which we actually did an extra step because all we needed to do was find the first 2 non-zero terms of the Maclaurin series. So this we get 1 minus, that's 9x squared over 2, plus we can have the extra term there because we're extra helpful. 24, 9 times 9, oh my gosh, 81 x to the fourth minus blah, blah, blah. So these two right here are our final answer. If you forget the Maclaurin series for cosine of x, you can always just build it back up. What we have to do is we find f of 0 plus f prime of 0 times x, the second derivative evaluated at 0 divided by 2 factorial times x squared, the third derivative evaluated at 0 times 3 factorial x cubed plus, and you keep up that pattern. So if you forget, you can just go ahead and calculate the derivatives, right? So we have f of 0 is equal to cosine of 3 times 0, which is equal to 1. So we know that our f of 0, which I can go ahead and replace right here, is equal to 1. Our first derivative, f prime of x, is going to be equal to negative 3 sine of 3x. So when we plug in 0, sine of 0 is just always going to be 0. So we know that actually the first derivative and the third derivative are both going to be sine terms. They're both going to go to 0. So let's go and find the second derivative. We get negative 9 cosine of 3x. And when we're plugging 0, so f prime of 0 is equal to negative 9. Cosine of 0 is just equal to 1. So we get negative 9. Let's go ahead and fill in these terms. So first we get 0. So these terms are going to go away. And then here we have negative 9. Negative 9 over 2 factorial x squared. And remember, we said that the next derivative is going to go to 0. So this is going to go to 0. And here we have exactly what we wanted, right? We have that this is equal to negative 1, positive 1 minus 9 halves x squared plus dot, dot, dot. So whichever way you want to do it, you're going to get the exact same answer. If you forget the Maclaurin series, you can always whip out the formula for a Taylor series, and you're going to find the right answer. But that's all I have for us on this exam today. If you enjoyed it, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see then. Thanks for watching.